In the last lesson, we looked at how the NMR phenomenon happens. So what happens to nuclei that have nuclear spin when we put it into a magnetic field? Well, this whole technique was developed by physicists. In fact, the people who first discovered NMR, Bloch and Purcell, received the Nobel Prize in Physics in 1952 for their discovery. So the important direction we need to go now is how can we use this phenomenon to glean information that is useful to organic chemists? Why are we talking about this in this class? So as we will see, although it'll take a couple lessons to get there, we can get information about the chemical environment of a hydrogen atom in an organic molecule based on the appearance of the peaks due to that hydrogen in the NMR spectrum. Okay, so the absorption of radiation at exactly 400 megahertz in a 9.4 Tesla magnetic field is only true for naked protons. That would mean a proton with no electron around it. But hydrogen atoms in organic molecules have electrons around them, and those electrons cause a shift in the required frequency of radiation to bring those nuclear spins into resonance. And that shift is called the chemical shift. Okay, so why is this? Why do these electrons cause a shift? Well, to a first approximation, and anybody who's a quantum mechanics guru is probably going to hate me right now because I'm simplifying this considerably. To a first approximation, we can say that electrons orbit around the nucleus. I know you learned in general chemistry that that's not what really happens, but let's just make that approximation right now, okay? Go with me here. So it's another law of physics that charged particles in circular motion will induce a magnetic field. Okay, I'm not going to derive that. I'm going to leave that to the physics professors. But as this diagram shows, at the position of the nucleus, which is of course where the spin flip is happening, the direction of the induced magnetic field due to the motion of the electrons is opposite to that of the external applied field. So as a result, we say that the local field due to the electrons shields the nucleus from the full effect of the external field. Okay, it's as if the field were not quite as strong in this location because part of it's being canceled out by the induced field in the opposite direction. Okay, so the resonance equation that we went over in the previous lesson has two variables, nu and b, the field strength. So we have two options to satisfy the resonance condition, correcting for the fact that there are electrons around a nucleus that induce this local field in the opposite direction. So the first way to correct for it is to make the external magnetic field just a little bit stronger. That corrects for the induced magnetic field, and you can keep your radio frequency radiation, your nu, at the exact same frequency to get a peak. Secondly, you can keep the magnetic field constant but decrease the frequency, knowing that some of the strength of the external field is canceled by the local induced field. The nucleus is observing slightly less of a field, so therefore it will come into resonance at local frequencies. I would like to, in the interest of full disclosure, tell you that modern NMRs don't do either of this. They utilize a third strategy called Fourier transform, but an understanding of how a modern NMR really works is beyond the scope of this course. Historically, however, as NMR was developed and applied to chemistry, you were able to do either number 1 or number 2. And it turns out to be a little bit easier to do number 2, so a lot of NMR's spectrometers were developed based on number 2. Okay, so let's take these ideas and apply them to an NMR spectrum. So here's a picture of a typical NMR spectrum. And as you can see, there are a bunch of peaks in different places in the NMR spectrum. And the reason that you get peaks in different places is because hydrogen atoms in a molecule, the different hydrogen atoms in a molecule, are in slightly different electronic environments. So how much the effect of the local field due to the electrons around the hydrogen atoms depends on exactly how electron-rich that hydrogen atom is. How much of those electrons really there around the hydrogen, or how much are they being pulled off a little bit somewhere else in the molecule? Which should bring you back to some ideas that we've talked about earlier in the course, like electronegativity and inductive effects and resonance effects. But we'll see all of that in due time. The rule for right now is that hydrogen atoms that are more electron-rich, if that electron is really sitting there around the hydrogen, they will be shielded more by the added electron density. Okay, so that induced local magnetic field will be stronger, and hydrogen atoms that are more electron-poor are shielded less. And the term we use for being shielded less is de-shielded. Okay, so looking at the spectrum then, electron-rich hydrogens appear on the right side of the spectrum, and electron-poor hydrogens appear further to the left. The right side is usually referred to as upfield, and the left side is usually referred to as downfield. And these definitions stem from the fact that historically, spectra were recorded using option 1 by scanning field strength. And a stronger field would be required to bring electron-rich hydrogens into resonance, thus the term upfield, whereas a weaker field, applied field, would be required for electron-poor hydrogens, thus the term downfield. Okay, so now let's look at the chemical shift scale. So on this NMR spectrum, on the x-axis you see the words chemical shift, then these letters ppm in parentheses, and then you see a scale from 0 on the right-hand side of your spectrum going up to 8 on the left-hand side of your spectrum. Okay, so the x-axis is labeled chemical shift, and 0 is defined as the chemical shift of the 12 equivalent hydrogens in the molecule tetramethylsilane, a silicon with 4 methyl groups on it, which is sometimes abbreviated TMS. Okay, so if the magnetic field strength is held constant, which it always is today, compounds that are highly shielded, such as TMS, will come into resonance at lower frequency. Most hydrogens in organic molecules are less shielded than the hydrogens in TMS, so we'll discuss this in more detail in the next lesson, so they will come into resonance at higher frequency. The chemical shift of a compound is a measure of how much higher the resonant frequency for a particular hydrogen is than the chemical shift than the resonance frequency of TMS. Okay, so the chemical shift scale is not an absolute scale. Chemical shifts of all hydrogens in all compounds are defined relative to that of TMS. Okay, so now what is a ppm? Well, we have said that the x-axis really talks about how the frequency changes between the resonant frequency of a particular hydrogen and the resonant frequency of TMS. So those frequencies, of course, are in hertz. Hertz are the unit of frequency, cycles per second. But the actual chemical shift in hertz, how much different a particular peak in a molecule is to where the peak is in TMS, actually depends on the magnetic field strength, which is somewhat of an inconvenient truth. So for the hydrogen atom in chloroform, CHCl3, if your magnetic field strength of your applied field is 1.4 Teslas, which would correspond to an operating frequency of 60 megahertz, the chloroform hydrogen is shifted by 436 hertz. If you move to the next lab and took the same NMR spectrum on a stronger magnet, on a 9.4 Tesla magnet, which corresponds to an operating frequency of 400 megahertz, then suddenly the peak comes at 2,904 hertz. Well, this is a bit of a pain in the neck, because there are so many spectrometers in use today with so many different field strengths. So what we do about this is to get a uniform scale, we divide the chemical shift in hertz by the operating frequency of that particular NMR in megahertz to get the chemical shift in units called parts per million. And the mega in megahertz is 10 to the 6th, is 1 million. So that's where the million comes from. Okay, so applying this to our example of chloroform, if you take 436 hertz over 60 megahertz, you get 7.26 ppms. And if you take 2,904 hertz divided by 400 megahertz, you also get 7.26 ppm. The important result here is that the spectrum, at least the chemical shift of a peak, will look the same regardless of the field strength. And that is really important, because you always want to be able to report the chemical shift of every hydrogen in every molecule as characterization data supporting the structure of that molecule. Okay, in the next lesson, we'll take this concept of chemical shift one step further and look at how the chemical shift, what chemical shifts we should expect for hydrogens in different functional groups.